Good afternoon, everyone. Welcome to the afternoon session of the third day of the Chennai Symposium on Gravitation and Cosmology. We have a few interesting talks lined up. The chair for this session is Nishikant Kandai from NICER, Bhubaneswar. Nishikant, over to you.
Okay, so welcome everyone, and for the afternoon session. So today's this session's first speaker is Beatrice Bonga from Radboud University. I will request everyone to keep your questions for the last 5 minutes, unless it's very urgent, in which case you just raise your, put your question in the chat box. So Beatrice, I'll indicate at 35 minutes.
Excellent, thank you very much. Yeah, thanks for having me. The pandemic is of course terrible, but the good part is that it's that I could easily join you for this Chennai Symposium. So I guess I can be happy for that. So in case you are expecting, gravitational waves and cosmology to be a talk about LIGO and data analysis, it will not be. I guess this will be more appropriately called. The talk will be more about the foundations of gravitational waves in cosmology. Nonetheless, I also hope that won't just be interesting for theorists like me, but also for people that actually work on LIGO and data. So let's jump right into it. But I think in all physics, I think one of the most valuable tools is perturbation theory, right? It's often incredibly hard, the equations that we have to solve. So what we do is we introduce, some type of background, some kind of, in GR, we typically introduce something like the Minkowski spacetime or the Kerr spacetime, or in cosmology, FRW spacetime, and look at small perturbations around it. Now, this tool is of, incredible value, but you should also note, right, that there's no canonical split. If I give you the metric on the left-hand side, say, for instance, the output of, a numerical code that looks at two black holes going around each other and forming a new black hole, right? There is really no, unique split into background plus small perturbations, right? I could come up with, some proposal, but you could, and you will likely come up with a different proposal. And that, of course, is a bit of a challenge if we want to understand what gravitational waves are, right? Because we think of this h mu nu as the gravitational wave part. So how do we deal with this? Well, one way to deal with this is to run away from the massy astrophysical, strong gravity regime as fast as you can. Right, so here gravity is wild, and particles might also be floating around, and we have these black holes and everything. But if you go far away, the idea is, of course, that your space-time curvature dies off, and you get to this more peaceful realm. And there, in that more peaceful realm, as a theoretical physicist, we can do our experiments, so to say, and study what gravitational waves truly are. Now, of course, you have to go very far away. So we go off all the way to infinity, but you should note that there are multiple infinities. So for instance, right, I can keep my space coordinate, say, fixed and send time all the way to infinity. So I would end up here. Or I could send, or keep time fixed and send r to infinity, ending up here. But one of the key insights of people that developed these new techniques to study gravitational waves was that actually the logical thing to do if we want to study gravitational waves, which like light, right, and like any type of radiation, it propagates along null geodesics. So the way to really study gravitational waves, it makes more sense to go to infinity along null rays, right, because that's also where all radiation ends up. So that's also what we'll do. So we go to infinity along these null rays. And that infinity we can call the radiation zone. Now these infinities, right, they don't quite fit on the screen. So, you should really be thinking of them as all the way of the screen. So Penrose popularized the trick to sort of put all these infinities on your screen, right, to make things finite. And that trick is known as a conformal completion. So the key idea is, right, to bring infinity to a finite distance. And the way to do that is, right, say that, I start with my original manifold, my original spacetime, right, with a metric on it. And in principle, right, all these points at infinity, which are not part of my spacetime, right? So for instance, right, if I were to think of the flat Minkowski metric, the points r at infinity, or where r equals infinity, are not part of your metric, right? Because that's where your metric diverges. So you don't include them, right? If you always write down your coordinate range, r is from or larger or equal to 0 and less than infinity. So what you do, but if you want to study exactly, r equals infinity, what you do then is you do this conformal completion. So you say, okay, well, let me attach all those points anyhow. And the way to make things, work well at the boundary is I'm going to rescale my metric such that, things are well defined. And I rescale my metric by a factor of omega squared. So if you want, you can think of this omega squared as being 1 over r, right? So that these points, that those infinities are sort of canceled. And now I have this new, bigger manifold, and I can study things all the way at infinity. And that's also what I'm going to do here. And if you do that with flat space, right, you get this hopefully familiar, but if not familiar, this is the conformal diagram of Minkowski spacetime. You get this nice triangle with the different infinities now being here. This is spatial infinity, time-like infinity, and this radiation zone is called scry. I think, Noor already mentioned that in the last talk before the break. And that, right, is that radiation zone is where we're going to study gravitational waves. Now, he studied it using the Bondi-Sachs formalism. I'll also get to that part, but there's another way of studying what happens near this radiation zone. And that way is somewhat more geometric. So I'm going to talk to you about that geometric approach as well. So if we study, right, gravitational waves, say in that context of, for instance, two black holes merging and emitting gravitational waves, or, in this picture, say a neutron star just doing nothing, and then it starts to wobble a bit, emits radiation, doing nothing again, then its space-time diagram, right, its conformal diagram would look something like this. And that's an interesting space-time too. Right? So what we now do is we say, okay, we can describe all these spacetimes, all these different spacetimes in one go. So we define this whole class of spacetimes and see if we can extract some general properties from them. Right? So, and this class of spacetimes we call that they're asymptotically flat. So the definition looks somewhat messy, but let me take, or messy, I mean complicated maybe at a first glance, but let me take you through it. Right, so we have, say we start with some physical spacetime, right, like we had before, just as in the picture, and we say, okay, that spacetime is asymptotically flat. If we can look at a slightly bigger spacetime, right, where this M is now that conformal completion with a new metric on it, right, and the boundary of that spacetime we call scry, and we demand that it has a topology of R cross S2. Well, that topology restriction is somewhat of a technical restriction, but okay, fine. So what we say, right, this metric, this conformally completed metric, is exactly the one you saw before in on the last slide. Right, so this is like omega squared G hat AB, and we of course demand that, since we don't want to work with stupid infinities, but we don't want to work with infinities, things are messy and stuff, and we don't want to work with singular structures and all that. We assume that they're both, that GAB now is smooth, and of course also that the conformal factor is smooth. And we also say, okay, on the boundary, and which I'll denote with this equal sign with a hat, right? So on this boundary, I require that this omega factor is equal to 0. So, because that's convenient, because then I can always locate where my boundary is. And then I also demand that its gradient is nowhere vanishing at this surface. And that is a convenient way, essentially, that guarantees for me that omega is a good coordinate that will allow me to also probe a little bit inside the space-time. Now, up until this point, right, point 1, actually, it's pure math in a way, right? I can do this for any space-time. There's no, I can do this for any space-time. Of course, there should be some smoothness requirements and things like that, but there's no physics involved, right? I could do this for any theory of gravity as long as it's a metric theory of gravity. But of course, right, what we want is the goal is to describe this whole wide class of spacetimes that are physically interesting. So what we now demand is that, of course, these spacetimes need to satisfy Einstein's equations. And right, we want the spacetime curvature to die off far away, right? We want things to become, somewhat flat far away. In other words, right, since the spacetime curvature is related through Einstein's equations with the stress energy tensor, right, we require that the stress energy tensor decays in a particular way. And, you can make that precise by saying that omega to the power -2 times the stress energy tensor needs to have a smooth limit. In some appropriate coordinate frame, this means essentially, right, if that this stress energy tensor needs to decay as like 1/r², at least. And luckily that includes many examples, right? Say Maxwell field, this is nicely satisfied. The scalar field, this is a minimally coupled scalar field, this is satisfied, etc., etc. Now, the cool thing is, what are the consequences of this, right? So this is just a definition. What can we get out of it? Right, so the cool thing is that Einstein's equations already tell us almost immediately that the normal vector, right, the gradient of omega, so that's the normal vector to this surface, is null on Scry. So Scry is in fact a null surface. I mean, it was already obvious from the picture, but the fact that this picture is correct is because of that mathematical background, right? And that also means that the induced metric on Scry has to be degenerate, right? So we denote that typically by being 0++ instead of, say, -++. Now you may say, okay, wait, but Beatrice, this thing sounds pretty interesting, all these mathematical techniques, but don't you have a lot of freedom in this construction? You said, okay, omega, you need some omega just to make things smooth on Scry, and it needs to be 0. But aren't there many other choices? And you're absolutely right, right? For instance, right, if I pick some omega and you pick, say, 3 times omega, then those are completely equivalent, right? Then omega would still be 0 on Scry, etc. So in fact, actually, we have a lot of conformal freedom. So this is in fact not just multiplying by some number, but this freedom is actually a complete functional freedom. And under that freedom, under the conformal freedom, also my metric changes, and therefore also the induced metric, and my normal vector changes, and they change in this particular way. Right, so here, the new metric will be omega squared, and my normal will be will be changed by omega inverse, which you can quickly check if you want to with this short calculation. Now, the cool thing about this is, right, that this induced metric and this normal vector, they're kind of like the stars of the show, right? They form the universal structure, and they're common to essentially all asymptotically flat spacetimes. So, of course, they're not unique, right, because of that conformal freedom. So any Q that is related to the one in flat spacetime, right, so just to the Minkowski metric, by some factor of omega squared, and some n related to the one in flat space by some factor omega inverse, they're all the same, right, because we have that conformal freedom. And every spacetime that's asymptotically flat, right, will share this structure. It's completely identical. this is pretty neat. Of course, right, then you may say, okay, well, but aren't we describing many different spacetimes at the same time? Shouldn't there be, something different at least? And of course, there will be things different, but they're encoded not at this leading order structure, not at this universal structure, but encoded in the next order structure. For instance, gravitational radiation will be hiding in the next order structure. And that, of course, should differ from space-time to space-time. So just, take the key points from asymptotics, right? Nowhere in the construction, right, from the definition or anything, did we introduce a split between, background and gravitational waves. Right? We did not say, well, we're looking at this as being small or anything like that. Right? But this split occurred completely naturally at null infinity. Right, where the universal structure, right, the Q and the N are acting like a background because that's the same for all of them. And then the first order structure is the one that contains radiation. And this whole description, right, the beautiful part, it's completely, fully nonlinear. So I also don't need anything like perturbation theory. So I'm really being true to what general relativity is, which is, right, a nonlinear theory. So I think this is like a really beautiful. I love this part, and that's why I think this framework of asymptotics is so incredibly useful. Now, if this was a bit mathematical and intense for you, all of this, what I said, of course, can also be said in terms of coordinates. Right? So in fact, this looks a bit messy, so let me get you some structure to it. You can say that any asymptotically flat spacetime, if you can find a coordinate system in which the metric takes this form, in fact, any metric you can write in this form, but now you also demand that these coefficients, these u, v, and u, w, that they satisfy a particular fall off, right? So any spacetime that, I can find some coordinates frame in which these things fall off like this is asymptotically flat. And what you see, right, is, if you go all the way to infinity, so in this case, that will be r to infinity, then at leading order, you get exactly flat spacetime. Not quite surprising, right? Because we've seen that sort of the induced metric at scry is exactly the same as the one in flat space. So that's not so surprising. And then at subleading order structure, you get all this other, physical interesting effects. Like, for instance, the mass aspect we see up here in this coefficient, which is exactly also where you would find, say, the Schwarzschild mass appearing. We have the angular momentum aspect hiding up here. And then radiation, or the radiative modes, are encoded in the 1/r part of this angular part of your metric. So those two definitions, right, the geometric description, a la Penrose and others, with the whole conformal completion, is in fact actually completely equivalent to the coordinate description, a la Bondi and Sachs. So that's quite nice. So you can choose whichever one is more easy for you to understand, or whichever one allows you to prove things more easily. Now, one of the things you can do with all of this is to study the asymptotic symmetry algebra. So there are two ways of saying what the asymptotic symmetry algebra are, right? Because we have these two equivalent definitions. So one is sort of to say, okay, well, these are all the space-time diffeomorphisms that leave the universal structure at null infinity invariant, right? Which is the statement up here. Or in terms of coordinates, which is probably slightly more intuitive, you would say something like, well, it is like the Killing equation, right? The Killing equation would be exactly like league C of G hat AB being 0 everywhere. But now we only demand that near infinity. So, we say it's only 0 at infinity, that's indicated with the hat, and we introduce some factor of omega squared to make things finite and stuff. So these two ways of thinking about the asymptotic symmetry algebra are completely equivalent. And what people found for the asymptotically flat case is that gives you the Bondi-Metzner-Sachs algebra, right? Which is bigger than Poincare, right? Because Poincare is just translations and rotations, if you want, but BMS is super translations and rotations. So if you look at it in terms of coordinates, the super translations are hiding here, right? So they're up here. So if I just had this function, this is now an arbitrary function of theta and phi, right, of my two sphere at infinity. But if it was just, one of the first YLMs, right? So only YLMs, if I were to decompose this in YLMs, right? Only with L equals 0, L equals 1, then it will be translation. But, right, there's no restriction in the BMS case. So it can be any of the YLMs, any combination. And then here we have the rotations hiding. Well, not hiding, they're quite in plain sight. Okay, here are the rotations. So now you may ask, okay, well, whatever, you have some asymptotic symmetries. What is it good for? What can I do with it? And I think that's a very valid question you should always ask yourself. Now, my answer to this is that it provides quantities with some physical interpretation. So for instance, right, if I look at the BMS group, there is a translation subgroup, and I can use that one to say what mass is and what linear momentum is, right? So I can calculate things, fluxes or charges, and I can interpret those if they're associated to one of those translation subgroup as the mass and the linear momentum. Similarly, for the rotations, I can define something called angular momentum, and then the super translations, they're shown to be related to the memory effect. So they also help me to understand that. So I think the BMS is having such an asymptotic symmetry algebra is incredibly useful. Of course, in this whole story, right, I was not talking about cosmology at all. I was, making a critical assumption, right? And that critical assumption was that as I move far away from sources, my spacetime, roughly becomes flat. That was sort of the key idea, right? Your space-time curvature should decay and things like that. And that, is very powerful. It buys me all these things, right? Like I have now the BMS symmetry algebra. I can use these 1/r expansions. I have my boundary Sachs coordinates, all like the good stuff. But of course, expanding spacetimes are not asymptotically flat, right? Because if we look at, say, this typical example of an Friedman, Lemaitre, Robertson, Walker space-time, then right, that it doesn't matter how far, if you look at a constant time slice, right, it doesn't matter how far away you go, your space-time curvature is the same everywhere at every other point, right, because the space-time is homogeneous. So there's no decay at all. So clearly these spacetimes are not asymptotically flat. So why do we assume asymptotic flatness, right? We know that we live in an expanding universe. So why do we make that assumption all the time? And this question actually was already asked in the 60s at a conference, to which Bergman, I think I like to quote these people because they said, Bergman said, the only answer I can give you is that these investigations, of asymptotic flatness date back less than 2 years, I believe. And people have simply started with the mathematically simplest situation. Quite typical, that's what we do in physics. And Bondi added, some additional words and then concluded with, I regret it as much as you do that we haven't gotten yet to the point of doing the Friedman universe. Quite surprisingly, somehow they never quite got around to it after that. And in fact, actually, the state of the art in cosmology is still to work with linear perturbation theory, right? So for instance, we look at either homogeneous solutions, which are quite useful to help us understand what goes on in the CMB, or, sometimes some people indeed look at the inhomogeneous solution to the linear equation to study, radiation from compact sources in, say, cosmological background. And when they do that, they use, on top of linear perturbation theory, they use the geometric optics approximation. But both of these, right, techniques are only linear. And the goal, right, or the idea, or what we hope to achieve is to see, okay, what can we learn from the full nonlinear theory in this setting? Right? Gravitational waves also should exist in cosmology in a sort of nonlinear way. And are there effects that we're missing? Are we maybe, should we expect to see some nonlinear effects that have either an observable imprint on our waveforms, or maybe they're not observable, but still conceptually important. So that's sort of what we set out to do. We said, okay, can we somehow adapt this framework of asymptotic flatness, which is completely nonlinear, to the case of cosmology? Now, in order to do that, we should know that there are expanding spacetimes. There are two different classes, right? We have the accelerated ones, like the current universe, and you can have a decelerated expansion where your scale factor still increases but slows down. Such as, for instance, the matter-dominated era that our universe went through, and the radiation-dominated era. So the radiation zones are quite different, as Jan already referred to, right? So if I have a cosmological constant and some accelerated expansion, your space-time diagram or conformal diagram will look like this, and your radiation zone will be space-like. But if you have an expanding space-time that's decelerating, your radiation zone will still be null. So just for the purposes of this talk, I'm not talking about this case, which is actually also very interesting, and lots of fun things have happened there, but I'm focusing on decelerating expanding universes. And the canonical example, of course, is an FRLW spacetime, right, where I have my physical metric, and I can always write it in terms of these conformal coordinates. So I write it as a scale factor squared times the flat metric, where the scale factor has this power law dependence on the conformal time, right? So with some power s. You wonder, okay, why s? Well, this s is related to w, and this w is exactly related to the equation of state parameter, right, which relates to pressure and the energy density of my perfect fluid. So for instance, if a W is 1, we have a stiff fluid. If W is a third, we have radiation. W is 0, there's dust, and W equals -1, you can think of as a cosmological constant. Now, for the spacetimes to be decelerating, we want this W to be larger than -1/3. Now, I don't like to work with things being larger than -1/3, so that's why we introduced S, right? Because S now is nicely between 0 and 1. And the case S being 0, right, that would just be, the scale factor would be just constant, V1, and would be flat case. So you can think of S being 0 as just a flat case, if you want, from now on. Now, the way to study, get a bit more intuition, of course, right, what we want to study all types of cosmological spacetimes in one go and understand their properties nonlinearly. But, just as asymptotically flat spacetimes are modeled after flat spacetime or Minkowski spacetime itself, right? We're first going to look at FRLW and see, what kind of interesting features can we extract from it, and can we then generalize it to more general cosmological spacetimes. So what we do is, right, we're going to make a conformal diagram. So for that, we need to do a coordinate transformation. Not particularly interesting, but you can do it, right? I just the details up there, and I need to choose a conformal factor. And what I then find is that I now have this simple looking metric, right, which is just FLW metric, the conformally completed FRW metric. Now I think it's much more useful to actually look at a picture. So this is what it looks like, right? So essentially, it's like half of Minkowski space, if you want, at least from the picture of from the perspective of the picture, right? So here we have scry, here we have our Big Bang, and this is the surface, of course, where we want to study radiation. And of course, I've chosen my omega such that it is 0 on all of scry, and that means, right, my omega is 0 whenever V is equal to pi, right? So keep that in mind. Now there's one problem. This construction looks wonderful, but near scry, if I expand my omega, I find that, near V equals pi, that omega scales like this, and that its gradient scales like this. So that means, right, that, as long as S is not 0, this is not smooth, right? Because this is a fractional power. And also, as long as S is non-zero, when V equals to pi, so at the boundary, this is 0. So that's not good, right? Because those were essentially the key two properties that we needed for that framework of asymptotic flatness to work, right? We wanted omega to be smooth and the gradient to be non-vanishing on scry, and now it's in fact actually everywhere vanishing on scry. So you may say, okay, well, let's fix that. And one way to fix that, right, seems kind of obvious, because I told you that there's lots of conformal freedom. So, you can say, well, Beatrice, you just picked a very bad choice for this omega. You should have chosen a different omega, say, omega prime. And, if you choose it cleverly, you can exactly, absorb all this badness, right? And then omega would be smooth at scry and the gradient would be non-zero. And that indeed looks wonderful, but as it turns out, then the conformally completed metric would diverge at scry. So it seems like you can fix something, but then somewhere else things go bad, right? And we, of course, like the whole goal of introducing these conformal completions was so that we don't have to work with diverging things, right? So we could just use, smooth tensor fields at infinity and just use our usual tools of differential geometry without worrying about singular objects. So this seems pretty bad, like what to do now. Luckily the solution is quite simple, and what we could do is say, well, actually, if you look at omega to the power 1 minus s, we see that that is smooth, and it still is 0 on scry, and its gradient is non-zero. So instead, what we do is we say, okay, we still complete the metric with our usual omega, but we just define the normal using this omega to the power 1 minus s, right? Because the normal you can always define up to some rescaling. So let's just use that, right? So we define the normal to be this. Instead of just the gradient of omega, we define it to be the gradient of omega to the power 1 minus s. And we introduce that 1 minus s for, simple scaling things, and we find that, of course, this gradient now it's nice and smooth and has all the wonderful properties that we want. So it seems like we're in business. But of course, there's another issue, right? Because if we study FLW spacetimes, right, there's matter everywhere, right? In the asymptotically flat case, we said, the stress energy tensor should, decay appropriately. But because of the FRW spacetime, right, there is no, since they're homogeneous, there is no decay. Matter is everywhere. In fact, if you look, for instance, at the trace and you take the limit to the radiation zone to scry, you indeed see that it's non-vanishing. But the situation is more challenging. You can even see that some of the components, in fact, are not just non-vanishing at scry, but in fact even diverge, right? Since S is smaller than 1, this is like, if you want, this is like 1 over omega squared, and this term is like 1 over omega, right? Yeah. Well, with some fractional power, but in any case, right, as omega goes to 0, this diverges and this diverges, and then the other terms are luckily finite. Let me not mention this part. So what we do now is, okay, say, well, we can't quite use this definition of asymptotic flatness, but we can look at this new class of spacetimes, which we call spacetimes with a cosmological null asymptote, and we essentially copy paste the definition that you saw before, but with 2 important changes, right? We say the gradient now needs to be defined differently with this minus s vector to account for the fact that, we at least want to describe FRLW spacetimes, right? Since these are the canonical cosmological spacetimes. And we need to make sure that the stress energy tensor has similar behavior. So we require that the trace exists and that, it can diverge, but only maximally in this form, which is exactly the same as I showed to you on the last slide.
5 more minutes.
Wonderful, good. So now we have this new definition and we can ask, hey, what is the asymptotic symmetry algebra, right? And what we find is actually, again, right, so these are the vector fields that leave my universal structure invariant. And I find exactly something that looks exactly like the BMS, but with some S dependence. And you may say, okay, well, but didn't we know that already? Because there was this paper in 2016 that said, hey, you know, BMS exists in cosmology. And as it turns out, there's quite a twist, right? Because as you can see, the super translation is going to again be written as some F times partial U, right? Where this F is some arbitrary function on the 2-sphere. But now it has a conformal weight that's 1 plus S instead of just 1. And you say, okay, well, that's super technical. I could not care less. Fair, but you should care, in fact, actually, because as it turns out, because of that conformal weight, there is no translation subalgebra. So there's no such thing as you know, saying, okay, this is a time translation, or this is a translation in the X or Y or Z direction. So it's not exactly BMS in cosmology. It's, you know, we have BMS-like symmetries in cosmology. And this is interesting, right? Because it has physical implications, right? Because what we did before is, if we wanted to find something like mass or linear momentum, we referred to the BMS group and we looked at this translation subalgebra. But now we cannot do that, right? Because there is no such subalgebra. So what does it even mean for a notion of mass and linear momentum? Can one even do this? It's also a challenge for extracting radiation. If you want, all you have to take away from this slide is that in the asymptotically flat case, there is this very nice property that you have peeling, which sort of introduces a very nice hierarchy between different components of your Weil scalar. And in this cosmological context, that's lost. You can show that explicitly, which a priori, I mean, doesn't mean that there's no radiation or anything. It just makes it more difficult to see what radiation is and give it a physical interpretation. Now, I think one key question you should ask, right, is, okay, your goal was to find many cosmological spacetimes and study, you know, their radiation and things like that. So, but you've only given one explicit example, FRLW. Do you have any other examples that fit within your definition? And the answer is yes, we can show that, in fact, the class of spacetimes that we defined is as big as the asymptotically flat case. The only challenge that we haven't been able to show is, you know, whether these spacetimes are physically interesting. So the proof did not allow us to show that. So that is still an open question. And in particular, what was actually also a very difficult problem in the asymptotically flat case, but we have not been able to show linearization stability. So that means, right, that if I have, say, for instance, FRLW and introduce some, if I wanted some linear perturbations, could I show that that spacetime is also part of the class of spacetimes? And we have not been able to show that yet, just because, you know, things are more complicated, matter terms floating around everywhere and things like that. So let me conclude. Right, we've seen gravitational radiation can be studied using asymptotics in the full nonlinear theory. Right, we don't necessarily need linear perturbation theory. And one of the key things that you can extract already sort of at the leading order, the universal structure, is that you have an asymptotic symmetry algebra. And this is very useful because it provides charges and fluxes with a physical interpretation. And the asymptotically flat case, that asymptotic symmetry algebra is the BMS algebra. But for these asymptotic cosmological null asymptotes, it's not quite the BMS. It's BMS-like, but there's no translation subalgebra. So that is kind of interesting, because that means, right, that we don't, as of yet, quite have a nice definition of what mass and linear momentum would be in this larger class of spacetimes that we would like to study. And there's ongoing work still with Beren Schneider, who's a master's student here at Radboud, and Janur, who you saw speaking earlier today on this. And we're trying to see, if we can fix any of these things and look at what are the properties of gravitational radiation. Thank you for listening, and I will be very happy to take any questions.
Okay, so let's thank Beatrice for the excellent talk, and we'll ask people to raise their hands, and I will get to you one by one. Questions. So Sumati Surya.
Yeah, thanks, Beatrice, for a really lovely talk. So it's incredibly interesting. I'm so glad that these discussions of the asymptotic flatness, things that we are used to listening to about scattering states and so on, are, they're seriously of importance in cosmology. So one of the questions, and so lots of questions, but I will just ask one, which is, can you say a few words about the implications of linearization stability or lack thereof in FRW for something like inflation, because that's something that assumes perturbative, that there's a meaningful perturbation theory. So that would be really interesting to, thanks.
Yeah, no, this is a great question. Okay, so I should maybe state it more clearly. We haven't been able to show this linearization stability in this context, but it doesn't mean that it doesn't exist, right? It's just very difficult to show. I mean, if things were not linearly stable, that would be pretty bad. But I have to admit that some mathematicians have worked on this in a slightly different context. So expanding spacetimes, FLW with like, say, a scalar field or things like that. And they have found that at least, the equations are linearly stable. But what they haven't shown is, which is kind of a difficult or a different question, whether then those new spacetimes that they study fall within this class of spacetimes that we have defined, right? Because that's sort of like the next thing you want to do. Once you understand.
There is also this work of, I think, Unruh and Loschek from a while ago on this. So I don't know if you're aware of it, but we can talk about it later. Yeah, possibly.
Isn't that within the context of but also quantum perturbations, right? That's in the context of QFT.
Yes.
Yeah. So this is all, I have to admit, this is all classical, right? So. You open up a whole new box if you introduce quantum effects, of course.
Of course, yeah. Thank you.
Okay, Amitabh.
Thank Beatrice for a very nice talk. So I wanted to understand the meaning of the statement linearization stability. In de Sitter case, there is a sense in which it is used the same words. A linear solution may not be a linearization of a nonlinear solution. Is this the sense you want to use this?
So the sense in which I want to use this is good. Is that right? If I have, say, FRLW and I were to introduce linear perturbations to it, can I show that new spacetime belongs to the class of spacetimes that I've defined? Yeah. That is the kind of linearization stability. Now, this is difficult, right? In the asymptotically flat case, there is this beautiful paper by Garage and Xanthopoulos in which they show that, if you take flat spacetimes plus linear perturbations, it's still an asymptotically flat spacetime. But the proof that they use, right, it's very non-trivial in a way, right? Because you cannot use the standard gauges that we use, right? So typically, if we study linear perturbations in flat space, we go to like a TT gauge or things like that. But that, if you use that gauge, it looks like perturbations on top of Minkowski space are not asymptotically flat. But it's all sort of a statement about gauge. If you go to the right gauge, which, even in asymptotically flat gauge, is like a very weird, non-intuitive gauge. But if you go to that gauge, then you can show that this is the case. So for us, we sort of have the same issue, right? There may be sort of like some natural gauges in which we could study linear perturbations on top of FLW, but in those gauges, it looks like these spacetimes don't satisfy our definition.
Okay. Okay. Thanks.
But that is probably, you know, more due to the fact that this is more a gauge statement than an actual physical statement, right? And we haven't been able to find the right gauge to show this.
Okay, thanks. I understand.
Okay, last question, Jahanur.
Yeah, hi Beatrice. My question is along in this direction of linearization stability. So, and by this linearization stability, you mean this Gerock and Xanthopoulos criteria, right?
Yeah, yeah.
Yeah, so, and yeah, so, and also you said that it is not you are not able to show that, right?
Correct. And the reason why we're not able to solve it is exactly because, well, because of all the matter terms floating around, right? That you know, in flat cases, matter decays near scribe, but in these cases, right, these cosmological null asymptotes, it doesn't, which just makes the equations very complicated.
Yeah, and also I have a comment that for the question for Amitav. So I think for de Sitter also it is not shown that if you just follow the Gerock and Xanthopoulos, I think the main thing comes into play, the asymptotic follow-up condition itself change. So Gerock and Xanthopoulos have some kind of follow-up, but that follow-up actually also doesn't suit for asymptotically de Sitter case. And I think the same problem happens in FLW.
Yeah. Thanks, Janur. I understood actually from Beatrice.
Yeah, so the asymptotic follow-up condition gate itself changed, and actually those are not consistent with the gauge Gerock and Xanthopoulos chosen.
Yeah.
Okay.
Yeah. Actually, yeah. Okay. Yeah, we can discuss later. Yeah. Actually. Yeah.
Sure.
Okay, so let's thank Beatrice again.